In these problems, we're finding some pretty tricky limits of these complicated-looking rational functions. And there are some techniques that you can apply that can help out in these cases. Although, if the techniques don't seem to work, there's kind of a rough and tumble method for calculating any limit you've got. And I'll show you how to do that when we get to the end here. But if you can apply some clever algebraic tricks, maybe rationalizing the denominator or rationalizing the numerator or some other kind of algebra so that you can calculate this limit easily, that's definitely the way to go. Look at this first one. We have the limit as x approaches 0 of this thing, and we've got x on the bottom. So this blows up. If we try to plug in 0, it's not going to work. So we want to try to manipulate this a little bit with some algebra. And I think what I'm going to do first is just try to simplify the top a bit by doing the subtraction of these fractions. So what I'm going to do is give them common denominators. To do that, I would need to multiply this fraction on the left-hand side by 2 over 2, and this one by x plus 2 over x plus 2. And that will give me 2 times x plus 2 on the bottom of both of these fractions. What I get when I do that, 2 times 1 on the top of this one is 2, and then I've got my minus sign, and we've got x plus 2, and then our common denominator now is 2 times x plus 2. When I distribute this negative sign, I get 2 minus x minus 2, and these 2's go away. So I just get a minus x over my 2 times x plus 2. But remember, this is all over x still. So at this point, what else can I do? Well, I can try to get x off the bottom of this fraction by multiplying by 1 over x over 1 over x. What that does on the bottom here, it gives me x over x, which is just 1. So that will disappear, and that's great. Let's see what it does over here on the top. I've got an x up here and an x down here, so they're going to cancel. This is really negative x over 2 times x plus 2 now times x, and that x will cancel, just like this one and this one did. So we end up with negative 1 on the top and 2 times x plus 2 on the bottom. That's a lot simpler looking than what we started with, and it has the advantage of me being able to plug in 0 for x without blowing things up. So if I go ahead and do that, I get negative 1 over 2 times, well, 0 plus 2 is 2, so 2 times 2, so that's negative 1/4. All right, so that wasn't too bad. Let's take a look at this next one. We've got the limit as x approaches 2 of the square root of x plus 7 minus 3 over x minus 2. And you notice if you plug in a 2 for x, the denominator becomes 0. I think in this case, the method I'm going to try is to rationalize the numerator. I've got x plus 7 minus 3. I'm going to multiply by the conjugate. Remember, we're using the rule of difference of squares here that says a squared minus b squared equals a minus b times a plus b. In this case, this is our a, and this is our b. So I'm going to multiply by the square root of x plus 7 plus 3 over square root of x plus 7 plus 3. So let's do that on the top. I'm going to get a squared minus b squared when I do that. Well, a is x plus 7, or the square root of x plus 7. So a squared is just x plus 7, which is pretty nice. And then b squared is 9. So I get minus 9. That's my a squared minus b squared. And then on the bottom, I have x minus 2 times the square root of x plus 7 plus 3. And you might think you should go ahead and FOIL this out, but let's wait a second and simplify the top first, because something nice is going to happen here. X plus 7 minus 9 is the same as x minus 2. And on the bottom here, we have a factor of x minus 2. So these can cancel, which is wonderful, because now we have a 1 on the top and this business, square root of x plus 7 plus 3 on the bottom. If I plug in a 2 for x now, I get 1 over the square root of 9 plus 3, and this comes out to be 1 over 6, and that's our limit. So those are a couple of examples using some algebraic techniques. I'm going to show you another one now that's pretty complicated, but we'll use a different technique. And this technique is going to work for any limit that exists. This one says, let the function g of x equal the limit as h approaches 0 of f of x plus h minus f of x over h, and then they give you what f of x is, and they tell you to find g of 7. So a lot of steps here. Basically what this is saying is take this f of x and plug it in up here. Once you've done that, plug in 7 for x and calculate the limit. This thing we're seeing right here, this is kind of a famous equation. This is actually called a difference quotient. It's the definition of the derivative, which you probably haven't gotten to yet in calculus, but that's something that'll keep popping up. But we're going to ignore that for right now and just calculate this limit in kind of a brute force way. Let me start by plugging in f of x up here. When I plug it in here, it's pretty easy. Minus f of x is just minus 9 over the square root of x minus 3. It's a little less obvious what f of x plus h is. What happens here is that the x becomes x plus h. So f of x plus h is 9 over the square root of x plus h minus 3. And this is all over h, and this is the limit as h approaches 0. Now, we want to find g of 7, so that means we're going to plug in 7 for x. So when we do this, we have 7 plus h minus 3. That simplifies to 4 plus h. So I get 9 over the square root of 4 plus h minus 9 over, and we're plugging in 7 here, so 7 minus 3 is the square root of 4. Whoops. And that's all over h. And the square root of 4 is, of course, 2, so this is 9 over the square root of 4 plus h minus 9 halves over h. Now at this point, you might be tempted to try some algebraic manipulation, and if you can discover a way to manipulate this so that you don't have h on the bottom and you can explore what this limit is as h approaches 0, go for it. But I want to show you a method where if you run out of your bag of tricks in algebra, you can still find this limit. Remember, h is approaching 0, so we can plug in some values for h, a handful of them, that get closer and closer to 0, and calculate these numbers by hand or with our calculator and see what number it's approaching. Let me show you how that works. I'm going to pick a number that's close to 0. I'm going to pick the number 0.1. And I'm going to plug that in here. So this means it would be 9 over the square root of 4.1 minus 9 halves over 0.1. Now when you calculate that, you get, something about 5.561, etc. And that's good. That's a good start. We have to do this several times, though, with numbers that get closer and closer to the value we're approaching in our limit. So let's try this with 0.01. If you do that, and I'm not going to write it all out here, you would get, oops, that's a negative 0.56244 and something else. And if you go a step further and go 0.001, what you would get is negative 0.56249. If you go further, one more step, you get something that's very, very close to negative 0.5625. And if you kept going, you'd find that you just get closer and closer to this particular value, and probably your calculator won't get you any closer than this. So this is the value we say that it's converging toward, and so this is the answer to this limit. And you could leave it as a decimal. If you want to convert this to a fraction, this happens to be negative 9/16. But this method of taking a series of values that get closer and closer to this value that h is approaching and actually cranking it through the formula here will get you the correct limit. So that's another method to find a limit. My name is Larry. I'm a teacher at EdVision's off campus. It's an online project-based school in Minnesota. If you're interested, you can check us out at lovethischool.org. Thanks.